find the unit tangent vector and the curvature for the following parameterized curve. So looking at this given vector-valued function that parameterizes the curve, I'm noticing that we have a greatest common factor of 4, a scalar multiple of 4. So let's just simply rewrite this parametric representation of C by pulling that scalar multiple out in front. So this is going to be 4 multiplied by the vector. Now notice the unit vectors on the components. So the x component is 0. So then moving on to the y component, this is t cosine of t minus sine of t. And then now the z component is just t sine of t plus cosine of t. Okay, so now that we've rewritten this vector-valued function, we're ready to find the unit tangent vector. So we'll keep in mind here, our unit tangent vector, capital vector T of that arbitrary parameter, is the unit vector pointing in the direction of the tangent vector. So we define this as the tangent vector divided by the magnitude of our tangent vector. So let's find the individual components of this. The first thing that we need is the tangent vector. So we need to differentiate that vector-valued function above. And again, I'm keeping 4 on the outside. 0 differentiates to 0. And now just be careful here. With this t cosine of t, we need a product rule. So that's going to leave us with 1 times cosine of t plus t multiplied by negative sine of t. And then the derivative of minus sine of t leaves us with minus cosine of t. So there's the derivative of the y component, and we already need a little bit more room. So now differentiating the z component here, again, be mindful that we have t times sine of t. So again, we need a product rule. So that leaves us with 1 times sine of t plus t multiplied by cosine of t, and then plus cosine of t differentiates to minus sine of t. All right, so let's quickly rewrite this so that it looks a little bit nicer. And wait, look at all this fantastic simplification. We have cosine of t minus cosine of t cancel each other right out in the y component. And the same thing happens in the z component. We have positive sine of t minus sine of t. So those terms cancel each other right out, which leaves us with the tangent vector defined as 4 multiplied by 0 minus t sine of t, and then we have positive t cosine of t. And we even have another scalar multiple that we could pull out. Notice how these two terms have a common t. So let's pull it out, leaving us with a tangent vector, a simplified tangent vector, 4t multiplied by the vector 0, negative sine of t, positive cosine of t. So if you didn't pull that scalar multiple out, please note you'll still get the same answer. You will just have slightly more exciting computation when we go to the next step and find its magnitude. So I encourage you, pulling a scalar multiple out like we did here always makes the distance formula a little easier. Because of our length of a scalar multiple rule, we can keep 4t on the outside of the distance formula. So here we go. We have 4t multiplied by the square root of 0 squared is 0. Then we have minus sine of t squared, which leaves us with positive sine of t squared, plus cosine of t squared, which is positive cosine of t squared. And we're delighted and excited because we recognize that this is Pythagorean's identity, and we know it is equal to 1. Oh, and shame on me, -1 on my test. Don't forget your scalar multiple in the front. That's 4t multiplied by the square root of 1, which of course simplifies to just 4t. So we have everything we need now. We have the tangent vector, and we have the magnitude of our tangent vector. So we can now use these two pieces to find the unit tangent vector. So we can say, therefore, our unit tangent vector, capital vector T, is defined again by the tangent vector all over the magnitude of that tangent vector. So plugging these individual components in, we have 4t multiplied by the vector 0 minus sine of t cosine of t. And that's all divided by 4t. And look at this beautiful simplification. 4t divided by 4t goes to 1, leaving us with the unit tangent vector, capital vector T of that arbitrary parameter, is the vector 0, negative sine of t, cosine of t. So this is part 1 of our solution. So now that we have the unit tangent vector, we're ready to go ahead and use this to find the curvature. So let's give ourselves plenty of room. So part 2, find the curvature. So our curvature, we can again recall, is of course defined as kappa, and this is equal to the magnitude of the derivative of our unit tangent vector with respect to the arbitrary parameter t divided by the magnitude of the tangent vector. So we already have the magnitude of the tangent vector. We found this above, 4t. We just need to go ahead now and find the magnitude of the derivative of our unit tangent vector. So we'll use the first part of our solution, and differentiating, we have the rate at which the unit tangent vector is changing direction with respect to that arbitrary parameter t is defined as the vector 0 minus cosine of t minus sine of t. And we'll use this now to compute the magnitude. So we're using that distance formula. So we have 0 squared is 0, negative cosine of t squared leaves us with positive cosine of t squared, plus minus sine of t squared is just positive sine of t squared. And again, we're so excited. We see, hey, that's Pythagorean's identity. So we know that's equal to 1. The square root of 1 is just 1. Woohoo! So we have everything we need. And we can say that therefore, the curvature, kappa, which is the magnitude of the derivative of that unit tangent vector divided by the magnitude of the tangent vector, is equal to 1 divided by 4t. And this is our beautiful final answer. This is our formula for curvature, and we can use this now to evaluate at any t value we want.